Yes, hello everyone, and welcome to our collaborative joint webinar of two strong machining partners. Today we will talk about the symbiosis of material physics-based analysis and cutting-edge machine tools to achieve optimum process conditions, and we will demonstrate on real-life examples of complex machining processes how we can drive machining beyond known limitations. My name is Julian Lüdecke from ThirdWave Systems, and I am the account manager for Germany, and I'm very happy to extend a warm welcome to our audience today. We have prepared a various number of aerospace, automotive, and general machining challenges to reveal the benefits of material-based feed rate optimization approach. We have divided our webinar into three parts. First, a short introduction, followed by a nice overview of Makino and a deep insight into some of their major strengths when it comes to heavyweight machining in aerospace. After that, my colleague Nishan Saini, who is the product manager of production module at ThirdWave, will talk about the different challenges and optimization potentials beyond cycle time reduction. And in the end, we will have some additional time for a Q&A session related to commonly asked questions from you, our audience. Before I introduce our partner and today's guest speaker from Makino, I would like to give you a short overview of who we, ThirdWave Systems, are and where we come from. Additionally, whenever you have questions, please feel free to write down your questions into the chat section. We will collect them during the webinar, try to answer them immediately, and discuss the most frequently asked ones in our Q&A sessions in the end. And now, I do not want to waste any more time. Let us make a start. Who is ThirdWave? ThirdWave Systems, or short, ThirdWave, is the premier provider of material physics-based FEA simulation and optimization solutions. We develop computer-aided engineering software to improve the development and virtual design processes of cutting tools and help manufacturing companies to get their products to market faster and improve their machining generally globally. Innovative companies, whether they are global players or locally acting smaller ones, use our solutions to dramatically reduce machining costs, accelerate design cycles, and improve product quality considerably faster than without ThirdWave. On the right-hand side, you can see our FEA simulation software Advantage, which is used to study and identify the optimum cutting tool design, which helps engineers to make decisions faster and understand the whys of cutting tool behavior. And on the left-hand side, you can see an animation of our NC optimization analysis software production module, on which we will focus on our webinar today. As you have heard before, we help companies globally, and so it's important to have a global presence as well. Our development and headquarters is based in Minneapolis, USA, very close to Chicago, and we have several distributors in the Asian market which deliver mother tongue language sales and support to our customers. And additionally, we have sales and support team in Germany as well, to which I belong to. Now, as you have seen where we come from and what our mission is, let us dive into our topic today and focus on our machining analysis solution production module. Maybe you have already heard about NC optimization or feed rate optimization software before, but let me give you a couple of more ideas why production module is different and helps to reduce cost per part with several approaches beyond just cycle time reduction. Because of our experience of more than 20 years in NC optimization, we are able to analyze and improve processes in a lot of different ways to dramatically improve tool life when that's your machining problem. The great thing about this, at the same time, we typically can reduce cycle times as well, although we maintain better tool life. But there's much more potential. For example, machine tool companies use production module to identify unstable cutting conditions which have a bad influence on the spindles or help to identify the correct machine tool concept for turnkey solutions. In our shop floor environments, it can help to answer or address operators' concerns and visualize the critical areas of the tool path. Other ways of utilization are the clamping or fixture design, and one of the biggest rocks for sure, part quality improvements with our roughness cap feature. As we, ThirdWave, develop software for virtual engineering, which helps with feed rate optimization, we need to work together with a strong partner, Makino, to achieve the best possible results or even exceed optimization results beyond known limitations. Makino, who are well known for their superior spindle technology and engineering expertise, is using our optimization solutions to drive machining beyond expectations. And now let me close the gap to our partner. I am very delighted to introduce our guest speaker of our joint webinar, Jonathan Garcia Barres. Jonathan is an application engineer at Makino and specialized on aerospace applications. He was born and raised in the north of Spain, where he graduated with a master's degree in mechanical engineering with specialization in manufacturing in 2014. During his last year at university, he participated in a high-level specialization course on machine tool technology, as well as worked as an intern at a local machining company which manufactures impellers and other aerospace components. After he successfully graduated in 2014, he moved to Stuttgart, Germany, and joined the Makino workforce as an application engineer in the aerospace business unit. His main task is to support customers across Europe producing aerospace engine components. As Makino is not only a machine tool supplier, they are also a solution provider, which includes activities like time studies, process design and optimization, test cuts, trainings, macro and post-processor development. I'm very happy to hand over the floor to Jonathan, and I'm sure he will provide a nice presentation about the world of Makino. Please, Jonathan, you have the floor.
Okay, so hello everybody, and thank you, Julian, for the great introduction. So first, I would like to start speaking about Makino and about the aerospace business unit. So as you may know, Makino is a premium quality machine tool builder, and its production is mainly located in Japan and in Singapore. But Makino has presence in over 21 countries in the world, and its market is divided in three main areas. We have Makino America, with headquarters in Mason, Ohio. We have Makino Asia, with headquarters in Japan, in Atsugi and Katsuyama. And we have Makino Europe, with headquarters in Kirchheim-Untertech, next to Stuttgart in Germany. So today we will focus on the European market. So here you can see the different locations of Makino within Europe, and in colors you can see the different business regions that from Makino. So the Southern Europe, which you can see in green, is covering all the southern countries. Then we have the Central Europe in purple, that is covering all the eastern countries. We have Northern Europe business region in orange, that is covering all the north of Europe. And finally, here we have the continental Europe that is covering mainly southern Germany, Switzerland, and Austria. So the headquarters of Makino Europe is located here in Kirchheim-Untertech. It's a small town next to Stuttgart in Germany. So here we have our biggest technology center in Europe and also our headquarters. And we have three different business units located here. We have the dial mold unit, production machinery unit, and the aerospace unit. If we focus on the aerospace business unit, we have our own showroom here with 1,250 square meters, and we have over 20 machining centers here. Also, me and my colleagues all together, we are an international team of 14 application engineers, and we give support or centralized support to all our European customers, even in their native language, if necessary. Okay, so now I want to explain the tasks from the business unit aerospace. So as Julian said, Makino is not just a machine tool builder, it's also a solution and technology provider for our customers. We are looking to work together with our customers and building a long-term relationship. That's why we are focusing on 5 main activities. The first one is the research and development of new manufacturing processes. So we always try to look ahead of our market and to look ahead of our customer needs and develop the right solutions for them. And secondly, we also work closely with all our partners and suppliers, sometimes even developing technology together with them. Our second task is to identify the optimal patterns for our machines. So basically, we analyze and we utilize the strength of each machine, and we develop the best strategies, and we find the most suitable products and markets for our machines. Also, here in our technology center, we develop and execute all our customer projects, test cuts, and time studies. In the same facilities, we also train our customers and also our employees in the best manufacturing practices and the best Makino products and solutions. We think that the knowledge and technology transfer is a key factor for our customers' success, so we put a great effort on that. And last but not least, we also use our technology center to exhibit Makino machines and solutions. So in general, any of our customers is invited to come here and meet our technologies and our people. And we have different kind of events. I would just to remark one of them is the Makino International Aerospace Forum. This is a forum that we hold every year around January, and we are showing Makino new developments and also our partners' new developments. So I invite you to come here on next January. Okay, but now switching back to the topic of this webinar, today I want to speak about the optimization of a blisk milling process. So as I said before, Makino is working together with their partners, and when it comes to optimizing processes, ThirdWave Systems is one of our key partners. So here you can see the part that we will optimize. On the left, you can see the raw material. This would be a turned preform, and we will optimize two different parts. One will be made of titanium, and the other one will be made of Inconel. On the right, you can see the finished part. It's a blisk with the blade height of 50 millimeter and the blade thickness between 0.3 and 1.5 millimeter. So the optimization will be done for the Makino DA300 machine, which you can see here. This is a 5-axis machine with a trunnion type table. And on this machine, we can mill the complete blisk in one setup. And also, I would like to remark that the maximum workpiece dimension on this machine is diameter 450 millimeters. Okay, so let's start first with the titanium blisk optimization. So as I said, the blisk will be milled in a single setup, and we have two different kinds of operations. We have a roughing that will be made with a solid carbide end mill, diameter 8, and we have semi-finishing and finishing that will be made with a solid carbide ball end mill, diameter 6. So the blade roughing and finishing will be done in 5 different levels, as you can see on these pictures. So basically, first we are roughing, semi-finishing, and finishing the first level. Then we rough, semi-finish, and finish the second level, and so on. We do that in order to keep the blade rigidity while finishing and avoiding chatter marks on the finished part. Okay, so now I want to present you the results of the titanium optimization, but before that, let's speak a little bit about the process. So this sample, it's a process that it's already an existing running process, and our target is to reduce the cycle time, but at the same time, we have to keep or improve the process stability, part quality, and the tool life duration. And as a constraint to the project, the tool path or the strategy will be maintained. So following this, so here you can see the previous cycle time divided in roughing, semi-finishing, and finishing. And now you will see the optimized cycle time. So for roughing, we reduce the cycle time in a 35%. On semi-finishing, we reduce an 18%. And the finishing process, we didn't optimize because we want to keep the part quality. So we don't want to change the feed rate. So altogether, we achieve a 19% cycle time reduction only by using the production module. And once again, I want to remark again that we didn't make any modification of the process or the toolpath. We only optimized the feed rate. Okay, but how we achieve this 19%? So to show that, let's start by the roughing operation. So here you can see the 5 different levels for roughing. The first 3 levels are milled with a diameter 8 end mill and 35 millimeter stick out, and the last 2 levels are machined with the same tool but with 55 millimeter stick out. Of course, because of the different stick out of the tool, the optimization criteria will be different for each. So let's start first about the air cut optimization or non-cutting optimization. This is the toolpath that you can see here in green. So many customers have issues with the CAM systems because they are not able to perfectly control the engage and retract movement and the non-cutting movements. And what is sometimes happening is that when the non-cutting movement starts, the tool is still engaged on the material, and this is leading to high cutting forces and tool damage. When we run a cutting force simulation of this process, we could see that in some levels there was a peak in the cutting force, and this is exactly because of that. The machine is still, or the tool is still engaged when the rapid movement begins. So by using the air cut optimization option from production module, so basically this option, it's automatically detecting when the tool is not in contact with the rest material and speeding up the feed rate in those areas. So only by using this module, we could increase the rapid feed rate from 1000 millimeters per minute to 20,000 millimeters per minute, and we reduced the roughing time by 21%. Additionally, I would also like to remark that this air cut optimization also allows to reduce the programming time, because basically the programmer doesn't need to make a perfect adjustment of the retract and engage movements. The production module will take care of optimizing the feed rate, and also the programmer doesn't need to check for a slight tool engagements during rapid movements. Okay, so that was about air cut optimization, and now we will talk about in-cut optimization when the tool is cutting the material. So on this example, I have the level 1 with a 35 millimeter stick out tool, and you can see here the tool path. So on the production module, we run the cutting force calculation, and we get the following tangential force over the time and the following load per unit length over the time. So the load per unit length is basically the cutting force divided by the engaged cutting edge length. So somehow it's a measurement of the pressure applied on the cutter. When we make the optimization for this, so first we limit or we optimize by the tangential force, and we set a value of 550 newtons. So with this, we will avoid all those peaks that go over that. At the same time, we limit the optimization by 350 Newton per millimeter on the load per unit length. And of course, because now we avoided those peaks in the cutting force, we can increase the cutting conditions because they are more stable. Okay, so now I will show you the result after the optimization. So you can see in red is the original process and in green is the new process. So now the cutting force will be limited to 550 Newton. And again, the load per unit length will be less than 350 Newton per millimeter as we programmed in the production module. Okay, and now talking about we talk about the first 3 levels, and now I will talk about the last 2 levels with the tool with the long stick out. And once again, we run the cutting force calculation, and the first thing we see is that there are some quite heavy peaks in the cutting force. Okay, and on the lower graph, we calculate the chip load per tooth or the chip thickness. So once again, to make the optimization, first we optimize the cutting force with 220 newtons. Like this, we can avoid those peaks. We will avoid the tool deflection or the tool breakage. And again, because the cutting conditions are more stable without those peaks, we can push the tool a little bit more farther, and we can optimize to 0.06 millimeter for the chip thickness. So now I show you once again the optimization results. So you can see in green that now the cutting force is under control and the chip thickness is never over 0.06 millimeter. So altogether, combining the air cut and the in-cut optimization, we achieve a 35% on roughing time reduction. And also it's worth to mention that we achieve a higher tool life because now the cutting condition is much more stable. Okay, so that was about roughing, and now I will speak about semi-finishing. So here you can see the tool path for the semi-finishing process. We have 5 different levels, and for all of them, we use the same tool, a diameter 6 ball mill with 52 millimeter stick out. So the challenge on the semi-finishing is that after roughing, the material stock is not regular. So as I'm showing on this picture, in some areas we have up to 1 millimeter material, and in other areas we have only 0.3 millimeters. This means that if we use a constant feed rate programming, we will have variable cutting conditions for the tool. It will have a different engagement and chip thickness on the different areas of the blade. And of course, without an optimization software, we have to program the most conservative feed rate, which may slow down the process. So here I'm showing you the optimization of the first level for semi-finishing. So once again, we run the cutting forces calculator, and we can see that there are some heavy peaks in the tangential force, and also that the chip thickness has small peaks, and also at the beginning is quite heavy. So once again, we will optimize by limiting the tangential force to 35 newtons to avoid any tool deflection, and we will limit the chip load per tooth to 0.018 millimeter to have a much more stable cutting conditions. So once we optimize this, you can see here in green the new result. So the cutting force is under 35 newtons, and we have a process with kind of a constant chip thickness, like 0.018 millimeters. So by using this optimization on the 5 levels, we reach 18% cycle time reduction for semi-finishing. And once again, we reach much more stable cutting conditions for the tool. So this will extend the tool life. Okay, so that was all about titanium. And now let's change to some serious stuff. So Inconel blisk optimization. So as you may know, Inconel is a nickel chromium based superalloy with very low machinability. And yeah, this material has a much higher tool consumption compared to titanium, and therefore the tool cost increased dramatically. So yeah, saving the tool cost and controlling the tool wear growth becomes much more important. And at the same time, the cutting forces are also considerably higher. So it becomes important to have control over the cutting forces to protect our equipment. Okay, so because because the Inconel has so low machinability, there are different ways of manufacturing Inconel parts. We can divide them in milling strategies that can involve different type of cutters, like a ceramic cutter, solid carbide, plunger, or disc cutters, and so on. Or we can have other strategies, non-milling strategies, like like EDM or electrochemical machining or water jet and so on. But today we will speak about the rather conservative process, and this is to use a diameter 8 high feed cutter in solid carbide for roughing. So using a high feed cutter has some advantages for the process. The first one is that, as you can see on the picture, so due to the geometry of the cutter, the radial forces are reduced. So we can use a tool with a longer stick out with the same tool deflection. Another advantage is that with a high feed cutter, we are programming very fast feed rate, but very low depth of cut. This means that when we run our roughing process, we can leave a near safe save stock on the blade after roughing. And finally, because we are using a solid carbide and not a ceramic tool, we can use coolant, and the temperature will not grow so much in the cutting area. So this means that we are able to leave even less stock after roughing without making thermal damage of the blade. So here you can see the roughing process. It's I mean, the overall process is very similar to the titanium one. And here you can see the toolpath. So in this case, we will make roughing in 6 different levels. For the first 3 levels, our high feed cutter has 32 millimeter stick out, and depth of cut will be 0.4 millimeter. And for the last 3 levels, we will have 55 millimeter stick out, and the depth of cut will be 0.25 millimeters. So here I'm showing you the optimization result of the first level cutting, as you can see here on the toolpath. And once again, we are looking for the same thing. We are trying to limit the tangential force to avoid the peaks with up to 800 Newton. And at the same time, we try to limit the chip load per tooth to avoid the peaks again and have like a constant chip thickness. So by doing so, we reduce the cycle time, but we can also increase the tool life. Okay, so here you can see the results on the Inconel optimization. So this is the roughing time on the original process, and on the optimized process, we made a similar optimization as titanium. So first, from air cut optimization, we gain 9% cycle time reduction. And for in-cut optimization, we gain 12% cycle time reduction. So altogether, we reduced the roughing time by 21% just using the production module. And we are able to increase also the tool life at the same time, because the cutting conditions are not so aggressive with the tool. Okay, so that was all from my side. If you have questions, please feel free to ask at the end of the webinar. And now, Julian, I give back the presentation to you.
Yes, thank you, Jonathan. That was very impressive. And yeah, before we come to our next speaker or our next section of our webinar, which will be held from my colleague Nishant Saini, who is the product manager of production module at ThirdWave Systems. He will talk about a couple of other applications and show some customer case studies in which production module help to solve machining problems. Before, I would like to ask our audience a question regarding their NC program creation, and let me launch the poll. And you should get the pop-up message on your screen right now. And the question is, do you create your NC programs yourself? And yes, with the CAM software. Option B would be yes on the machine control, or C, now we get finished G-code. Looking forward for your feedback. We will give it a few more seconds to receive all the answers. And yeah, and a couple of another one. I think all the attendees have answered the question right now. I will close the poll, and it's 50-50. The half of the attendance is using a CAM software, the other half is using finished G-code. And thanks for your feedback. And now I will give the presentation rights to my colleague, as I've mentioned before, Nishant Saini, the product manager of production module from ThirdWave Systems. And yeah, now, Nishant, would you mind to take over from now on?
Thank you, Julian. I'd love to take over. And thank you, Jonathan, for a good overview of the titanium and Inconel machining, and in fact, quite a bit of depth, I should say, not only the overview. So let's move to the the remaining section of the presentation. Like I said, I should say, like Julian said earlier, one of the core capabilities is to reduce cycle time while maintaining tool life. And this is what you saw in the presentation from Jonathan, where he was all the while trying to make that trade-off between cycle time and tool life. And production module is a good tool to make the analysis, understand exactly where the challenges are, like the high chip load area or high force area, and decide what approach the user needs to take. What I should mention is that there are many more uses of production module for an engineering analysis of a tool path. So addressing tool wear specifically, right? Here we are striving to get the right tool life. In tool wear cases, we are solving a problem that was there for tool wear issue. Could be a problem with spindle life, or you want to make sure your load and torque are in check for the machining process. So I'm going to do is I'm going to cover examples around these areas which are not typically focused on cycle time aspects, but you'll see a constant theme where we are covering both aspects and much more in terms of part quality, tool wear, and spindle life as well. All right, with that, I'll move on to the next slide. So the first case study that highlights this is a case study from our customer Leistritz, based out of Nuremberg, Germany, working on the aerospace engine components, and they're well known for very high surface quality finish and for very small geometry tolerances. So this business, they made quite a name for themselves in this area. And one of the areas that they were using production module, as you can see, it says example 1. There are other cases they used it, but we'll focus on the vane segment, where the tie 6.4 was being machined and the surface roughness requirement was 1.6. And most importantly, there was no rework by hand allowed in this case. I should also mention they were using CAM systems like the NX and the Concept NREC, and TurboSoft Plus. So different CAM systems for different analysis was being used. However, their focus right now for the analysis using production module was improving tool life and eliminating chatter mark. Obviously, surface quality is something that they cannot compromise regardless. So that was the intention of the analysis. And in this analysis, using production module, what you will see on your screen is a chart on the right-hand side, which highlights the cutting forces before the optimization, which is in red, and cutting forces after the optimization, which is in green. And you can clearly see here the trade-off was made that we will machine a little bit longer, but make sure that that tool life is improved. And as you can see, the improvement in tool life was there from 2 parts up to 7 parts. At the same time, what you will also notice is that there was an overall cycle time savings. Like I mentioned, this is for a specific operation where it was better to trade off cycle time for tool life, but overall they were able to save cycle time throughout the process. So that's an important element of doing this what if scenario analysis in production module, rather than doing a trial and error approach on the machine tool. The next part that they wanted to address was related to, oh, sorry, I think I moved one slide too fast, was address chatter marks near the fillet. And prior to using production module on this particular case, there were different tools tried, different process conditions tried. But as you can see that any kind of adjustment on the shop floor, you'll see that there's a significant spike of forces again in the original tool path. And that's where production module can help by adjusting and breaking down the tool path to have the appropriate feed rate for each section. And by reducing those forces, they were able to address the or remove the chatter marks completely in the fillets. Again, overall cycle time was also improved because there were areas in the tool path where the efficiencies could be gained separately. So this is a good example of where the focus was making sure that you have a high part quality, removing the chatter marks, and also make sure that the tool life is addressed without compromising the cycle time. The next is actually a case study from Makino itself, Makino USA. Jonathan is with Makino Europe. We worked with Makino USA as well. And in this case, it was about understanding what the machine could do from an automotive customer standpoint. In a fairly large T1 machine, something interesting about this machine is that when the axis is in a -90, it can go behind the backside of the pallet by about 50 millimeters. So giving a large reach, and that's something that the machine was unique in terms of the solution it provided to the customer. Where production module helped was understanding of 3 different operations. So we'll start out with the heavy roughing operation, where the primary mode of consideration was material removal and the spindle power. So the customer was looking to make sure, or I should say Makino was looking to make sure that the overall roughing process, which is where you have the most power consumption requirement, was well within the continuous duty cycle. So as you can see, the green line is the continuous duty cycle, the red line is the heavy duty parts requirement, which could be a spike that the machine needs to handle. But we are well within the continuous duty cycle, which is important from a machine stability standpoint, as well as making sure the part quality is good. Now, moving forward, there were specific areas of operation. So in this case, a high feed mill was used with a long reach. And when you have that kind of a scenario, reaching out into this pocket while trying to traverse this distance, you will want to make sure that there is no concern about the bending moment. With the long reach, that can always be an issue. For this HSK 100, Makino knew that the 45 kilonewton of clamping force is what it had. It allowed for a bending moment of 1,250 Newton meters. And then it was translated to what is the side load this process can take, or this tool can take at that long reach. Clearly, with the help of production module, what they did is made sure that any areas where there were spikes which exceeded that load limit in the XY resultant force. So depending on which direction you need to look at, production module provides that answer, and they made sure that the machine did not exceed that at any given time on a long basis. So that's an important element of again reducing the trial and error, coming to the right answer in an effective manner. The next portion of the tool path was unusual tool path and geometry to come along with. So what I mean by that is it's a tool that is reaching into this section. So you see the radius that is being ingrained here. This is the first one, the second one inside, the third, and the fourth. Now, typically the process is to have an estimate based on the overall material removal rates. But in complex tool paths, such as this one, at different orientation, it becomes difficult to make those calculations using a calculator. You need to have the actual material removed Boolean so that you understand what exactly the chip load on the tool is at. And in addition, if your insert shape is not a standard insert shape, that itself can cause difficulties in calculating manually what the loads would be. Again, production module was able to help out in this scenarios where there were 3 passes taken, and the spikes that you see on the XY resultant force were reduced considerably. Again, in some cases, you will give up some cycle time, but I think that's a reasonable trade-off to make sure that the longevity of the machine, the tool, is considered in the overall cost per part aspect. I'll move to another case. This is on the automotive engine block side for casting, where the coming in variation was significant enough that the customer had 20 spindles or 20 Makino machines, and 15 of them were running absolutely fine, but 5 of them required a look at the spindle every 6 months or so. So Makino went in and said, hey, this doesn't make sense, so let's figure out what's going on. And surely what was found is that there is a significant variation in the casting stock coming in, and that's something that's a production reality, right? You can't run away from that. It is going to happen given the process that we have. So what we need to do is plan for it, and the way you would plan for it is that you would model it in production module using the max material condition, right? You know, okay, now I can get up to this much, so the stock variation can be handled inside of production module for this die-cast part. And what you realize as soon as you do the analysis is that while most of the tool path is okay, but there are certain sections where the force peaks up, clearly where the gates are, where the material flow is coming into the cast part. And with that analysis, understanding what the machine capabilities are, Makino then modified the tool path to take out all those spikes, even in the worst case scenario, right? It's not about the standard, but it is in the worst case scenario, and made sure that the machine was within the process was within the machine spindle limit for 15 kilowatts. What you'll notice in this case, however, is that the original chip load was constant, but here we have a significantly varying chip load with a max limit to it. So it's not completely free. However, it's more important to look at the power consumption, the bending moment, the force analysis. So there's a lot more that goes into that analysis than looking at perhaps just a specific area. So, and again, an area where machining process analysis using production module was helpful. I'll take another case study on the Blisk machining side, similar to what Jonathan had presented, but with our customer GE Aviation. And in this particular case, there were concerns both about perhaps some programming errors, could be a little bit of a mistype of feed rate, and also looking at what the tangential force and the chip load needed to be. And the goal here was maximizing tool life, I think, because any disruption to the production process is clearly more of an important consideration in this scenario. And the results in this particular one were 2 to 3.5 times the original tool life, and the cycle time again was maintained to the baseline, which means what was running in production prior to the analysis. And there were not only cost savings from a tool life perspective, but there was also cost savings from reduced disruption to the process, right? Because if you have 10 or 18 cutters, 10 or 18 inserts per tool, if even one of them has an issue, you got to change the entire thing, and that can cause disruption in the process, and the probabilities go up with more loads there. So it was important to make sure that the cycle time wasn't impacted. However, there were enough cost savings from the standpoint of reducing the production disruption. And then I'll come to my final case, and I've said this one is my favorite one because again goes in to show how a production module analysis can help in solving perhaps a long-standing problem. And in this case, there were part burns due to cutter failures, and the users thought that perhaps the blanket feed rates that one applies were not the right approach for solving a problem that they were facing. They were using standard tool paths from various CAM systems, CATIA and NX. I should mention we have interfaces to connect with this. So if you have analysis tool paths there, you can bring them in fairly quickly into production modules for the analysis, and then use that for the post-processing. What I wanted to show here is a screenshot of an operator report on the operations or the sequences that were being machined. And as you will notice, in the last 3 ones, what they had was they were breaking cutters at 100%. So decided to run at 80%. Clearly, production needs to go on, and they need to find a way to do this. And the way for them to do it was, well, we got to reduce it to 80%. In the next one, it was again breaking a cutter, but it was a new cutter, in fact. So it broke at 80%. Now they were not left with much option, and they had to run it at 60%. Again, a similar kind of a scenario with the last operation as well. This shows the challenge that the operators face, and you clearly need to address their concerns on the shop floor. And analysis with production modules showed, one, where the excessive load on the tools were, and it also showed why it was there, because the axial depth in this particular case was very high. Again, multiple approaches were used. You can always do what-if analysis using production module. So while production module itself doesn't change tool paths, you can always program a new tool path and see how it compares to the previous one that you were running. So in this case, what you see as blue are the forces after the optimization, and what you see earlier or in the red are the forces before the optimization. And clearly, if you reduce your peak loads by about 60%, you would expect to address those problems, and which they did. At the same time, they made sure that the cycle time was within the acceptable limits. The interesting part here is that when they were running the programs at 100%, had the programs run at 100%, their intended cycle time was 124.5 hours. But in reality, they were running at 80% or sometimes even lower. So what they were achieving on the shop floor was 150 hours. Once they optimized using production module, they were able to achieve 119.5 hours and were running at 100%. So they didn't have to, the operators didn't have to sit on the machine, sit there, hey, no, I want to listen what's going on. Maybe the cutter will break. But they felt like it was running very smoothly after the optimization was done. So if you look at it at 100% versus 100%, so what I mean by that is an optimized program by ThirdWave, when compared with the original program, if it was running at 100%, we were still saving 5 hours. But in reality, they were running at 80% or even less. So save 30 hours or more than 30 hours in this particular case. From a throughput standpoint, not necessarily cycle time, but from a throughput standpoint. So I hope that gave a sense of the ability to address part quality problems, like I mentioned with Lystrit's case, the tool wear issues which were addressed both for Lystrit's and GE, the spindle wear case for Makino's customer, where they were getting casting variations that were not originally expected. And then the load torque analysis and the bending moment analysis that Makino had done for high material removal rate kind of scenarios, and scenarios where we know that the long reach tools can have problems in operations. And finally, the operator concerns that you saw, GKN had to address in their cases. So that was the summary of some of the applications. What I want to leave you with is a thought on, okay, now what is it on the technology side that drives this analysis? And it's important to understand the technology that runs this is not a cutting test technology. It is a material understanding technology, and that's what the core focus or excuse me, the core capability of ThirdWave systems is. We are able to understand machining at a fundamental level. And what I mean by that is that in your machining, you're machining at elevated temperatures, anywhere from 500 to 800 degrees C, depending on what material you're machining. So as the material heats up, there is thermal softening. it gives you the ability to push the tool faster. But there is a competing effect, which is the material will harden the faster you push it or faster you are machining it. So there is strain hardening effect that comes in. So you have to make that trade-off between thermal softening and strain hardening. And to do that, you need to understand fundamentally how the materials work, which is what our FEM capability advantage provides. And that is made available to our users through a material model in production module, which is run for the analysis here. So that's the technology that drives this analysis that you have seen so far. And I'd say that's all I have to present. I will like to hand it over to my colleague Julian to take us to the next few steps.
Yes, thank you very much, Nishant, and for sure to Jonathan as well for this deep insight of the scientific approach and symbiosis of two strong partners who evolve the full potential of each software and hardware together. And as I've mentioned before, we have a third section or a fourth section, a Q&A session. But before we go ahead with this, I would like to ask our audience one or two another polling questions to understand your opinion regarding what we've seen so far and for sure regarding the current business situation. Let me ask, what do you consider to be the highest priority? Is it A, the optimization or reduction of cycle times, B, reduction of tool wear, or C, process stability? Or we are really interested in your feedback. Yeah, looking forward to your answers. Okay, we have received a couple of answers. I may give you just a couple of more seconds to collect all the remaining votes, and I think we are almost through and looks good. I will close the poll, and the feedback you gave was 2/3 are looking for cycle time reduction, which leads to a lower cost per part. I think that makes sense, but given the current business situation, for sure process stability is very important as well. Let us go right away to the next polling question. I'm looking forward to your feedback as well. The question is, if you would use production module, where do you see more potential? Is it A, the optimization of existing or running processes, or is it B, the support of programming, as Jonathan mentioned, for new projects? Okay, yes, we have received the votes, and I'm closing the poll. It's 33% are looking for optimization of existing running processes, and 36% would utilize production module for new projects like programming support and so on. That's very much that's very interesting, and I thank you for your participation on the polling questions. And now let's come to our Q&A session. And during our webinar, we have collected a lot of questions, and I hope our audience can understand that a few of them go too much into detail and would probably, or the answer would probably exceed our remaining time for the webinar. For those questions which we are unable to give an answer right now, we will ensure to provide a personal feedback to each of you after the webinar. So, but there are some general questions as well, which came up on my head too, and I'm sure they are interesting for every attendee as well. Jonathan, the first questions or the next questions are going to you. Would you tell us what the typical steps for the process development at Makino are? How do you act when a customer gets in touch with you for the first time?
Okay, so when a customer contacts us to produce a new part or a new family of parts, the first thing that we do is a feasibility study and we offer to the customer the right machine for their products or for their product. After that, we can make a time study with a cycle time estimation and a process and fixture concept. And after that, we will proceed according to the customer needs. So some customers, they want only technology transfer from us. In that case, we will make like a customized application support for them. Other customers, they want to make a test cut, and then we can make a CERKey. So we make the project together with them. And finally, there are other customers that just want to have a turnkey that we provide everything to them. But normally we don't recommend this way because we think that involving the customer during the test cut is much better for their success because they will get to know really well their machine capabilities.
Yeah, so you would like to transfer the knowledge and understanding of the process to the customer, so he's able to act accordingly when there are issues left, and so they can work on this on their own and act independently. That's interesting. May I ask you the second question right away? How do you identify the perfect or best process conditions for the tools that you use?
Okay, so for the starting cutting conditions, let's say we have three different ways of approaching them. The first one is, of course, based on our own experience and our previous projects. So normally, either we really know the material that we will machine, or if it's new for us, we check the chemical properties or mechanical properties, and we adjust the conditions accordingly. The second way would be for very critical operations, for example, like heavy roughing, we check the limits of the machine and we program the cutting conditions according to them. When I talk about limits, I'm talking about the maximum cutting force or radial force, axial force, or bending moment, spindle power, spindle torque, and so on. And finally, it's also important that, as I said before, we are working very close with our suppliers, and especially when they are developing new technologies, so we test them together with them, and we can see the potential of these new technologies. That's how we find the starting cutting conditions for our projects.
Yeah, and you mentioned a couple of issues or processes where production module fits very well and probably helps you a lot with identifying this the best process conditions. Let's go to the next discussion section or next question. Which specific alloys do you typically deal with, or what's the most challenging, or have you different ways to work on specific issues?
Okay, so normally we deal with very normal alloys for aerospace, like aluminum, for example, the 70 series, or titanium, Inconel 718, and so on. And regarding the machine, I have here our machine portfolio. So here you can see all the machines that are dedicated to aluminum, and you can see the x-axis travel and the y-axis travel. So this is, let's say, the length of the part and the height of the part. And as you can see here on the small dimension machines, normally they are multi-purpose machines with different spindles available to cut different materials. And then if we start from the Mach 1 and bigger, normally these machines are highly focused on aluminum milling and high MRR. So on these machines, we have HSK F80 and 130 kilowatt spindle with 33,000 RPM. So they are very focused on aluminum. But that was about aluminum. And for titanium and superalloys, once again, I'm showing here let's say, the length of the part and the height of the part. We have small machines, which are these ones are using HSK A63. And once again, the small machines are normally multi-purpose with different spindles available. Then we have bigger machines with HSK 100, And then we have our strongest machines with HSK 125, and these ones are highly focused on heavy roughing of titanium and hard materials.
Yeah, okay, yeah, thank you very much. Or would you like to add something?
No, it's fine, I think.
Oh, okay. Yeah, you talked a lot about your spindles, and before we come to to my last question to you, I have some preparation question for our audience. Again, a polling question regarding spindle lifetime and spindle maintenance. And let me launch the poll at the webinar to ask our audience: how often do you have to replace or remake spindles on your machines? A, every 6 months, B, approximately every year, or C, more than 4 years spindle lifetime? Looking forward to your answer. Oh, I can see there's a small mistake in our polling questions for sure. A would be every 6 months, B is every year, and C every 4 years. And but we've collected a couple of votes already. 50-50 every 6 months, and the other half is has voted more than 4 years spindle lifetime. That's pretty good. Yeah, I will close the poll because we have collected all the necessary information to go to our last and very last question. As I've mentioned before, one of the major strengths of Makino and one of their big points, USPs, is the spindle technology. And sorry, Jonathan, could you tell us what's so unique and special about your spindles?
So yeah, as you may know, the Makino spindles are designed and produced in Japan. So they are designed and produced by Makino itself. So this has many advantages. So one of them is that the spindles are designed right for a machine or for a material. Okay, and the second advantage is that Makino has a deep understanding of their spindles and its limitations. So we can recommend the customer how to treat the spindle, let's say, and how to reach a much higher spindle life. So just for you to know, we have customers that are using the same spindle for more than 20,000 hours. This would be around 5 years in a 2-shift configuration. And we have customers that are using even more time than that, like double, 10 years. But important is to have a control of the cutting forces and don't overload the spindle and treat it well so it's lasting and producing with the required quality.
Yes, thank you very much for your answer on the last question, and thanks very much to you, Jonathan, and Nishant, for sure. It was a great pleasure to talk with you today, and I hope our audience now has quite a good understanding where and how they can optimize their machining process by picking the low-hanging fruits. And yeah, we are happy to follow up with our attendees, but for sure you are very welcome to get in touch with us via email, LinkedIn, phone, at the Makino Aerospace Forum in January, or at upcoming shows. And that's all from me. Have a nice day, a great week, and for sure, take care. Best regards.